working in the data lab at ProRail, where he's investigating the possibilities of new data and technologies to improve the rail in the Netherlands. In the FOAS project, ProRail used acoustic measurement data from underground cables for many different cases, one of which was to find the locations in the track which limit the maximum train speed. So the talk is about fiber optic acoustic sensing, which is directly related to what I just mentioned. So the floor is yours.
Yeah, thank you. So the correct pronunciation of the name is Joost van Schip, but it's really just a mess for anyone who is non-Dutch. So so I'm going to talk about fiber optic acoustic sensing, which is a relatively new technology, which can be used for all sorts of use cases. So I work at ProRail in the innovation department, and there we get to play with all the nice new data innovations and see how we can apply them to all sorts of use cases. So just to elaborate a bit on the technology, we did some tests with a so-called interrogator unit. This interrogator unit you can attach to a fiber optic cable, which is normally used for telecommunication or just anything that needs to transmit data. And as long as there are some free fibers in there, you can attach this interrogator, which will send pulse of light throughout the cable. And based on the reflections in the actual fibers, you get an idea very locally up to 1 meter resolution of very small modifications or vibrations that have an impact at that location. So it has a spatial resolution of about 1 meter. It's 2,500 pulse of light a second. So it really gives a very wide view of in both resolution and also in space. And it's also a lot of data. So for 5,000 data points, it's 10 million points per second. So we're talking about terabytes per week here. Vibrations. We use it for many use cases. One is trespassers, track defects. We also are from ProRail, so we actually look at trains as well. And the one I'm going to focus on today is the subsoil stability. One big advantage of the technology is that fiber optic cables are basically everywhere, or at least close to train tracks. They're being used for telecommunication. So whenever there's a sensor, you can basically employ this technology. So that has a huge potential. So we did 2 test cases, both of around half a year. So these are 2 locations in the Netherlands with about 10 kilometers of track. And we monitored very closely, especially in this piece. And that's what I'm going to be talking about. And here you can see the picture of the interrogator. It's attached to the cables. So critical train velocity. Well, to give a brief outline of the problem, everything is more, better, and faster now. So some of the train tracks were built like 150 years ago in the Netherlands. And based on the current traffic and also larger vehicles, faster trains, some of the subsoil is actually good enough to actually carry the trains. So that's why there is a current solution, which is MASW surveys at specific locations. They give locally very specific information, but it's a lot of manual labor. So we're going to talk about a data-driven way to approach this as well. So this is what the data looks like. So here we can see the distance and the time. And here we see stuff moving through time, which is a train, and here's another train. And basically the intuition about maintaining getting the actual subsoil is when you look at a train passing a fixed location, which is like a horizontal line. Here you see that the vibrations in the ground are moving at a faster rate than the train. Luckily, otherwise you get all sorts of resonances and dynamic loads and all sorts of unwanted stuff. And when you look a bit further, you can see that the actual arrow is getting a bit steeper. So you can already see from this very simple visualization that in different locations, the waves in the ground move at different speeds. And yeah, so how can you quantify this along the entire cable? Just to give a bit of an intuition, we look at the bow and tail waves, and also when the train is passing. So when a train is coming at you, or well, at the track you're standing next to, you can already feel the ground vibrating, and that's the sort of vibrations we're looking at here. And yeah, you can visualize how fast they're moving. You can transform this data when you have enough samples of passing trains into a so-called phase velocity spectrum. And this phase velocity spectrum gives the energy in many different frequencies and at which speeds they occur. And yeah, you can already see this green line here. So over here, yeah, if you go any faster than 200 meters per second, it's going to be a problem here. Well, I don't know of any trains that actually reach this speed. Yeah. So once you have this phase velocity spectrum, there's some quite involved technique to invert it into an actual soil decomposition, or at least the strengths of the soil at different levels. And then you get plots like this, which basically say which is the maximum velocity which is allowed at different levels in the soil. And what we found during our tests, which we did together with Deltanis, by the way, yeah, the technique using the Swallows cables gives very comparable results to the MASW measurements that have been used so far to investigate this sort of thing. So yeah, you can get all nice pictures of the soil decompositions based on this technique alone, and they compare pretty well with the actual known decompositions. Yeah, to give a bit of conclusion, so falls can replace the MASW surveys as they are, but yeah, you can do a lot like along 5 kilometers each time you place this interrogator. Yeah, and it just gives a much larger reach. And yeah, it has also been published this weekend. So if the slides are shared, you can also look into a bit more detail yourself. So yeah, that's what I want to talk about for the trackability. But for us at ProRail, the interesting thing is that this technique or this interrogator can also be used for many other different use cases. Yeah, I can't go into detail in them all, but yeah, we used it to find trains, which we actually needed to see when we had to look at bound tail waves. You can use it for well, or at least we tried this, but that turned out to be a bit harder in practice to actually get insights on the quality of the tracks. You can get ideas of how the actual trains are performing. So if they're like square wheels is what they're unofficially called, they give large impacts, and you can also see it in the data. We also developed a neural network approach to find trespassers, where you can see each individual footsteps of people close to the tracks. So that's another development also done in this year. We looked at level crossings, so cars and trains and bikes passing by level crossings, critical train velocity, and another big one in the Netherlands is digging mammals. Like badgers and beavers especially, they burrow underneath the train tracks, and that can give instabilities, and it has reached the news a couple of times already. So yeah, no, that was my talk. So are there any questions?
Thank you very much. there is immediately